Can you see the screen, the slide?
Yes.
Hello, I'm Jongwan, GSI in the X281. And today I will cover the binary tree and AVL trees. And yeah, let me start with the announcements. So the project is due June 9th, and Lab 7 is due June 12th, and Lab 8, which is this one, is due June 19th. And the reading problem for this Lab 8 is the due date of it is June 12th. Oh, before we move on, do you have any questions on this? Okay, I'll just move on. So this is the last week's handwritten problem. And so the task was to change any word in the sentence that starts with the prefixes into the prefix. And so the kettle becomes cat, and rattled becomes rat, and battery becomes bat. And you needed to do this in this OPM plus NM square time. Here are the common mistakes that you can take a look at. And this is the solution for this. So basically, you have to go over every word in the sentences. And for each word, you have to go over you have to put every characters in the word into prefix and check whether it's in the set or not. So your unordered set that contains the prefixes should be initialized with the range-based initialization like this. So do you have any questions on this? Okay, yeah, let's move on to the next one. So today I will talk about the trees and tree traversals. And the most important data structure that I will cover is binary search trees. And AVL trees is a variation of the binary search trees that balance the trees. And yeah, I'll cover these three today. And let's start with the tree traversals. So these are the tree terminologies. So root is the node with the no parents, and leaf is the node with no children, and internal node is all the other nodes except for root and leaf. Oh no, it should include root. Sorry about that. And the depth and height is defined as a distance. So distance from a node to the root is depth, and distance from a node to the lowest leaf node is height. And siblings are nodes with the same parent node. So this is the struct that represents each node in the tree. So it has a pointer to the left and right, and it has a value, and this data structure can be used to build a tree. And for the warm-up question, we have the task of finding the minimum depth. So I'll give you like 1 minute to think about how to do this. If you have any question in the meanwhile, please ask me. Okay, I guess we can move on to how to do this. So basically, we have to, in the tree data structure, what we usually do is to traverse over every node and do some tests. So in this case, we check whether the current node is root because we want to find the depth of the binary tree, so minimum depth of the binary tree. So we have to compute the distance to the root. So so if it is not if root is empty, then we should return 0 because there is no so the root is the null pointer. And if the root contains left, so if the left of the root is empty, then we should return the right of the root plus 1. And if the right of the root is non-empty, then we should print out the minimum depth to the left +1. And then else, if these both cases are not true, then we should print out the minimum of both of them. So in the traversing the tree, there are 4 different ways to order the nodes. And let's take a look at the first 3. So in the pre-order, we first traverse the parent and then left and right. So left is always earlier than right, but when we put the parent, define this order. So in the pre-order, we first visit parent and then left child and right child. In the post-order, we first visit the children, so left child and right child, and then we visit the parent. And in order case, we are visiting parent in the middle. So we first visit left child and then parent and right child. And in level order, it's a little bit different because we are visiting the first root, and then we visit the next level, which is the direct children of root, and then we visit the direct children of those children. So they're going over all the levels in the descending order. And within each level, we have to traverse from left to right. So this is the basic recursive tree traversal structure. So so we are given the head as an argument here, and then if head is null pointer is not null pointer, then we are returning things, and then we go to the then we traverse through the left and right in order, and depending on where we put the code in these 3 possible choices, this can be pre-order, in-order, or post-order. So if we put, for example, if we put the code in the bottom part, then it becomes post-order because we first visit left and then right and do some task on that left and right, and then do the task for current node after all left and right children are traversed. So for example, let's say we put the print node in before we traverse to the left and right. So this one should be pre-order because we are doing some task that's related to the head before we actually go to the left and right. So this is the example tree, and what happens? What would happen if we run the code just we saw in this code, in this tree structure? So this is the pre-order traversal. So we start from the root, and then we print out the it is pre-order. So root is the parent, so it is printed out first, and then it goes to the left and right children. And then let's say we went to the left subtree. So we are at node 6, then it is still, we have to traverse in pre-order. So parent 6 should be printed out before we go to the left or right children 4 and 7. So if we do the pre-order traversal, then the order should be like this. So it's 15 first, and then the root of the left subtree, which is 6, and then root of the left subtree is 4. And then there is no more left child for 4. So we go to 5. And then we are done with the left subtree. So we go back to 6 and see the right child of it, 7. Then we can do the similar thing to go over all the 3 nodes here. Do you have any questions? If you have any question, you can cut in while I'm talking. So yeah, let's move on. So the post order, as I mentioned before, the task is done after we traverse through left and right. So if we print the node after we traverse through left and right, then this is post order. And let's do the same exercise in this same tree using the post order instead of the pre-order. So in the post order, we still start at the root, but we don't print out the root, but we visit the left and right children first before we print out the 15 here. So that means we just we don't print out 15, but we call the traverser for 6 first. And then in the 6, we call the traverser for 4 first. And then in 4, well, we call the traverser for 5 first. So that means 5 should come first. And then the next one is 4. And we go to the right child in 6, and then 6. So the post-order traversal of this tree, it has a sequence like this. And in-order traversal is printing out in the middle of these two traversal to the left and right child. So if we are doing the in-order traversal, we can just print out the left side first, and then print out the middle, and then right. So the order becomes this. So we start from 15 again, and then we print out the left subtree first, and then in the left subtree, we also print out the left part, which is 4. And then since 4 is the parent, it should be printed out before the left child, which does not exist. So 4 is the first element here, printed, and the next one is the right child of it, 5. And then we go in the order like that. And then this is the example of the lever order traversal. So when we are doing lever order traversal, we cannot use the same template, but we should use Q to put the children before we move on. So let's say here we define the level Q, and then we push the head. And since there is no, the level Q is not empty at the beginning, it goes into this while loop. And then the level Q dot top is first head. So top is head, and then we push the left and right child of this top into the level Q if it exists. And then it goes into this while loop until the it is going to it loops until the level Q is empty. And if you think about it, when we are printing out this top, that means top just got popped out from the level Q. That means all the parent level of the top is already printed out. And since we are pushing left first and then right, the left to right order is also in this level order traversal. So what is the level order traversal of this tree? So we also begin at the 15. So we first pop, then 15 comes out, and then we print out the 15. And then we push the left and right child, which is 6 and 23, into the Q. And then since there is an element in Q, we go over 6 and 23 and print 6 and 23, and push all the children of these two nodes into the Q again. So the while loop does not end until it gets to the final leaf of this tree. And the order is 15, 6, 23, 4, 7, and 71, 5, and 15. So these were tree traversal methods. And let's do the practice using this. So given a root to a binary tree, find the level of the tree with the minimum sum. So each node has a value, and then we want to find the minimum sum of it. But the binary tree is not guaranteed to be complete. So complete means that for let's say it has level 2, then complete tree should have every end leaves so every leaf should exist. So it's not guaranteed to be complete because there in this example there is no right child of 2. And we want to find the minimum level sum, and we want time complexity of O(n) and memory complexity of O log n on average. So yeah, let's look through the code here. So basically, we have to do the same similar level order traversal. So we first given the root, we put this push into the queue, and then we go over the while loop as before. And then so if queue is not empty, then we find the level size, which is queue.size, and then we initialize level sum into 0, and then we go over every element in the level. So when we were the code for the level order traversal popped out one element at a time, but in this case we pop out all the level. So we popped out level size number of elements, which means that we are popping out every node in that level, and then we go over every node in that level and compute this level sum, which is just the accumulation of the temp that element, which is the temp is node that just got popped out. And then for every node that we traversal, we still need to push left and right children into the queue because we want to go over every level. And if the level sum is smaller than minimum sum, then this is the minimum sum. So we replace minimum sum with the current level sum. And then we go over, we increment level after we go through one iteration of this while loop. Okay, so yeah, sorry. I think this one is complete because it's filled out in from the left to the right until this point. And then the purpose of temp is that, so these temp is going over every node. So let me just first talk about this for loop here. So this for loop at the beginning, this I is going over the 0 to level size -1. And the level size is the current the number of nodes existing in the current level. So and the nodes in the current levels are all in the queue at the beginning of the for loop. So if we pop out so if we find the front queue.front, then that is the current node in that level. So we are going over every node in that level, and this temp represents the current node in that level. Does that answer your question? So basically, this while loop is a little bit different from the level order traversal we just saw. And in each while loop iteration, it's going over one level. And in one level, there can be multiple nodes in there. So we are going over those nodes using this for loop. And this temp represents the current node in that level. So yeah, that was the tree traversal. And if you have any question, I can answer right now. Okay, let's move on to the tree reconstruction. So now the task is given the traversal, this in-order and post-order traversals, we want to reconstruct the tree. So what do we know about the last element in the post-order? So in the post-order, we are printing out the parent at the last. And in this sequence, the last element should be the root. So 1 is the root. And then what do we know about the elements to the left and right of the node in the in-order traversal? So every element in the in-order before 1 should be in the left subtree of the 1. And every right elements in after 1 in the in-order traversal, it should be forming the right subtree of this tree. So elements to the left are in the left subtree, and right are in the right subtree. So these 4 elements should form the left subtree. And then given these 4, 8, 2, 5, basically these are also forming the trees. And inside this tree, post order is still preserving the post order of this subtree, which means that among these 4 elements, the last one should be the root of the left subtree. So yeah, we put the left subtree. Yeah, and then we can recursively do this. So we mark 2 in here, and left part is left subtree, and right part is right subtree. So the 5 is right to the 2, and 4 and 8 should be left to the 2. But among 8 and 4, 4 is letter in the post order. So 4 should be the root in the left subtree. And then in the in order, 8 is on the right of 4. So it should be right child of 4. So we can basically do the similar thing for the 6, 3, and 7. So we can reconstruct given in order if we have some additional assumptions. So if the tree is complete, then we know that given the in order, we can reconstruct the tree given just in order traversal sequence. But if we don't have those kind of assumptions, then we need both in order and post order, because it's difficult to know which is the left subtree and right subtree given the post order only. And given only the in order, we can't find the root because it can be extremely imbalanced. So for example, in the in order, given the same in order traversal here, another valid tree is starting from 4. All subsequent elements are the right child of the previous one. Okay. So these were the tree traversal and reconstructions. So let's move on to the binary search tree, which is the main data structure I wanted to talk about today. So in the binary search tree, you can think of it, you can correspond this to the in-order traversal. So every left subtree element should have the key smaller than the current node. And every right subtree element should be larger or equal to the current node. And the reason why we are using that is that, so for example, if we are given the tree that has a very balanced structure, then we can compare the current node. So let's say we want to find specific value. Then we can compare that value against the current node to find this element. So yeah, we can know that whether this element is possibly in the left subtree or right subtree by comparing ones, and that comparison is at most log n, because if the tree is fully balanced. So yeah, here the main task is the insertion, lookup, and deletion. And all of these tasks on the average case should take log n time. But there are extremely bad case, which is just extremely imbalanced case, which has just chain structure. So in that case, if we want to find the last leaf of that chain structure, then we have to go over every nodes in the tree, which takes all of n time. So that is the worst case. And then in the same chain structure, if we want to find the non-existing element that can be found by comparing just once with the root. So it should exist in the left subtree of the root, but it actually does not exist. Then it takes O of 1 time. Yeah, so let me repeat this. So in the insertion, we start at the root and traverse downwards until a spot to append the node is found. So for both insertion and deletion, we first need to find the specific location that we want to insert or delete. So we basically do the search in both cases. And then if we find the point where we want to insert our element, then we can do additional tasks to do that. And for the deletion, we also can, so if the node has, if the target node that we want to delete has one child, then we can replace it with child and delete the child. And if the node has two children, then we can replace it with one of the child and then remove the target node. And when we have two children, there are two ways to select which child to replace the current node, the deleted node. And it's called in-order successor and in-order predecessor. So predecessor means the left child, and successor is the right child, because in the in-order, left child is just before the parent node, and right child is just after the parent node. Yeah, so let's do some example here. So we want to insert these 4 elements into the currently this current tree that has 3 nodes. And if we want to find, if you want to insert the 3, then we first look for the 3, which if we begin at 8, then 3 should exist on the left subtree of this 8. And then when we are at 4, it should also be at the left subtree of 4. And then we could not find any elements at the child of the 4, so we put 3 in there. And we can do the similar thing for 5. So if we want to put 5 in here, then we compare it against the root, and then we know that it's on the left subtree. And then we compare it against 4, and then we know that it should be on the right side of the 4. And there is no elements in right subtree of the 4. We can put 5 there. And we can do the similar thing for 6. So for 6, we start at 8, and we go to 4. And 6 is larger than 4, so it goes to right, and then again right. So 6 should be the right child of 5. Yeah, there is a question. I don't quite see why we need to assume the tree we're gonna reconstruct from a in order is complete. I think we can construct any BST. If you are referring to the reconstruction, sorry, let's go back. Yeah, in the tree reconstruction, oh, okay. So I mentioned that we need both in-order and post-order traversals to reconstruct the tree without any additional assumptions. And if we have additional assumption that the tree is binary search tree, or if it is complete, then we can just reconstruct using just in-order traversal. That was what I meant. So if we just want to, if we want to reconstruct just from in-order traversal, then we need additional assumptions like the tree is binary search tree. That is another assumption that can make in-order traversal to be reconstructible. Yeah. So yeah, we did 3, 5, 6, and then 9 should be on the right subtree of 8, and it should be on the left subtree of 10. So this is 9 is placed here. So this is the insertion of the binary search tree. So binary search tree itself is very simple. So I'll be moving on very quickly. So we want to delete the 5, 4, 8, and 11. So if you want to delete 5, 5 is found by, again, traversing from 8 to, so 5 is smaller than 8, so it should be on the left subtree. And then it's larger than 4, so it's on the right subtree of the 4. And then we found the 5. So now we want to delete 5, but there is a child of 5. So we are deleting this 5, and at the same time we replace it with the child, which was 6. And then now if you want to remove 4, we still need to traverse this tree to find 4. But if we remove 4, there are 2 options. So we can replace 4 with the in-order predecessor, which is 3, left child, or in-order successor, which is right child. So it becomes, there are 2 possibilities. So it is okay as long as you're using this consistent choice when we are deleting. But yeah, we have to use one order for every time. So let's move on to deleting 8 here. So if we want to remove 8,
can you explain deleting 4 again?
Excuse me?
Can you explain deleting 4 again? Kind of
okay.
Yeah.
So here we want to remove 4 here.
Mm-hmm.
And then we have to replace it with some any of child here, right? Because we need to keep it connected. So we have 2 choices. Excuse me?
You could replace it with 3 or 6.
Yeah, we can replace it with 3 or 6.
Is there a way y'all want us to do it, or it doesn't matter?
It depends on the application. So
okay.
Yeah.
All right, depends. All right.
Yeah, it depends.
Thanks.
And yeah, let's move on to removing 8 here. So when we are removing 8, 8 also has 2 children. So we have to, we again have 2 choices. So before we only, the subtrees were just 1 node. So we can just pick left child or right child. But in this case, there are, subtree has more than 1 node. So we have to find the in-order predecessor and in-order successor, which is the number that is just before 8 when we are doing the in-order traversal, and just after 8 when we are doing in-order traversal. So that is 6 and 9. So there are 2 choices like this. And then the 2 choices will result in this. So we are replacing 8 with either of it, and then we are removing the root 8 because we want to remove 8. And then now, at last, we want to remove 11, but 11 does not have any child, so it's simple, just we can remove it directly. So this is the deletion for binary search tree. So yeah, here are 2 questions to think about. So what does it mean for a tree to be balanced or unbalanced? And what does this mean for the insert and search complexities? I think I already gave out the answers, but anyone have an opinion on this? Okay, so tree is balanced if the left subtree and right subtree has similar height. So in this case, we are restricting it to be differ by at most 1. And what does this mean for the insertion and search in the binary search tree? Which means, so basically, if the tree is balanced, then all the traversal to find specific elements takes log n time. But if it's extremely unbalanced, like chain that I mentioned before, then the worst case complexity can be O of n linear time. So we want to use the log n time insertion and search. So we would like our binary search tree to be balanced, but it's not guaranteed always because it depends on the order of insertion and deletion that we perform on the tree. So that's where the AVL tree comes in. So is there any question on the binary search tree? Okay, if not, I can move on. So I was curious, so I looked it up, but this AVL tree, the name of it came from the inventor of this tree. So this is the self-balancing binary search tree, and it maintains balance with each insertion and deletion. So basically, we are performing three instructions, three functions on this binary search tree, which is insertion, deletion, and search. And search does not change the tree structure, so we only need to think about the insertion and deletion. So search is exactly the same as the binary search tree. So since we are using the self-balancing binary search tree, average and worst case search, insertion, and deletion complexities are all log n. And there are two invariants. First one is exactly the same as before. So we have so all the node numbers are in order, and the balance factor is limited to -1 to 1. So this is the definition of the balancedness that we just saw. So it's the height of the left subtree minus height of the right subtree, and it can take value. It can take only integer values. So we are restricting our balance factor to be -1, 0, or 1. Okay, so basically, insertion and deletion starts exactly the same as binary search tree, but we are doing additional operations to make it balanced. I think this text is not a good way to learn this, so let's move on to the example. So basically, when we perform the insertion and deletion as before in the binary search tree, then we'll get some tree that is possibly unbalanced, but still has the in-order, the node order is correctly placed. So we only need to think about the case where the tree has this correct order, but it's imbalanced. So if it's balanced, then we are done. So we can move on to the next operation. But if it's imbalanced, we are doing some additional operations to make it balanced. So let's say currently our tree looks like this. So when we think about the node 4, then the left subtree has height of 3, but right subtree has a height of 1. So that differs by 2, which means it's imbalanced. So we have to do some operation. So all the operations to fix the imbalanceness is called rotation. So basically, we rotate right in here to make it balanced. So yeah, so in the node 3, we are putting the left child of it into the place where node 3 was there. And then we put the node 3 into the right child of node 2. And then symmetrically, if the tree looks like this, then we do the rotate left to correct for this. But the problem is that we have other cases like this, so we cannot do the rotate directly. So in this case, we can have simple correction, which is rotate left first based on the node 1, and then do the rotate right. So we have to perform 2 rotation in this case. And this is also the symmetric case for the case. So case 1, 2 is symmetric and 3, 4 is symmetric. So in this case, we perform rotate right first and then rotate left on the parent of, so rotate left based on this node 3 to get the final balanced one. So these 4 are very simple cases, and the last case is the most complicated case. So before we could just rotate because there were, so let's see this example. So we could rotate, yeah, let's see this one. So we could rotate because node 3 did not have left child. Since left child of 3 was empty, we can put 3 directly into the left child. And then in these cases, we could easily fix this into the previous form. So those first 4 cases are very easy. This special case is a little bit more complicated because we cannot directly rotate to get the balanced one. So basically, we want to rotate to put 4 into the parent of 2. But the problem was that 4 had a left child, so we cannot put 2 into 3 position, the location where 3 is in the previous tree. So the way to resolve this is to move 3 into the right child of 2. So that's the new rotating map. And the reason we can do this, yeah, I think there is a slide for this. Okay, yeah, let's first go over the process here. So we first disconnect the left subtree so that these now the connected part of the tree can be rotated. And then after rotation, node 2 always have right child empty because 4 was previously child of the 2, but now it's moving up to the parent. So now we can connect node 3 directly to the left, directly connect to the node 2 as a right child. Yeah, so how do we know there is room for 3 there? And what about 2's right child? So 2's right child is always empty after the rotation because 4 was the right child of the 2 before, but now it moved to the parent. So we can directly put this 3 into node 2. So basically, all these operations can be thought of as the rotation. And there are some edge cases that we have to deal with, but you can think of it as just rotation with some edge case dealing with edge cases. So is there any question before we move on to the practice problem? Okay, so now let's do the practice problem here. So we are given this tree, and we want to delete node 5 and 7 in this order. And then assume that we use in-order successor. I will go over step by step, but before that, you can think of how to do this. So you first remove, so we have to remove 2 nodes from this tree. So we first remove as we did before, as in the binary search tree, and then we do the rotation to correct for the imbalances. I'll give you 1 minute to think about it. Okay, let's go over this example together. Let me use the So first we want to delete 5 from here. So let's say we remove 5 here. Then since we are using in-order successor, 6 should replace 5. So now it becomes 6, 3, 7, 8, and then 1, 4, 2 as before. And then is this balanced or imbalanced? It's still balanced because the height of the left subtree and right subtree differs by just 1. So now let's say we want to remove 7 here. Then I'll just remove it. And then we can just directly replace it with just 8. Like, oh, sorry. Yeah. 8 like this. Now it's imbalanced, so we need to do the rotation to fix it. And the way we fix this is to, so given this root node, we know that left subtree has the height of 2, but right subtree, the left subtree has the height of 3, and right subtree is 1. So we have to rotate from 6 here. So we first put 3 as a root, which was the left child of the previous root. And then we have to put 6 in the right subtree. And then we now have to put 8, which was originally the right child of the 6, so it should be stay there. And then now we know that the left subtree of 3 should be in that order, so it should stay the same exactly as before. But now the problem is to where to put this 4. So we know that 6 had the left child as a 3, and now it should be empty there. So we are putting 4 in there. Yeah, that was the process of doing this. Do you have any question on this? Okay, then let's move on to the slides again. So this is the answer. And let's move on to the handwritten problem now. So the task for the handwritten problem is to compute the diameter of the tree. So we want to find the diameter of the tree, and diameter is defined in the general graph structure as the maximum number of edges on any path connecting two nodes of the tree. So actually this definition is general one that also works in the general graph, but in the tree we can find it more efficiently compared to the general graph. So let's see the example here. So in the first example, the diameter is 8 because the path from L to M is the longest one. And then there are 4 edges from L to A and another 4 edges from A to M. So there are 8 edges total. So diameter is 8. So in this case, the longest path goes through the this root node, but it might not be always the case. So in the second example, it does not go through the node A, but it exists in the subtree. So this happens when it's not complete tree. And the path also can start from root to the leaf, as in the third example. So here, the task is to build a function, recursive function, to find the diameter. And we need to do some kind of traversal. Oh, excuse me. So the task is to implement the function that computes the diameter. So we should use the recursive structure to build the current diameter based on the diameter of the left subtree and right subtree. And the implementation can be O of n squared, and that's the requirement. But it can also be O of n linear time if you think really hard and do it efficiently. I think that's all for today's lab. And if you have any question, I will be here to answer your question. But yeah, I think I should stop the recording first.